Okay, so now we are going to derive our Fletcher equation. Okay, so for that we assume a simply supported beam which is subject to some load. Okay, so a load P applied on the structure, and we have got simply supported, so therefore we have got reaction R1 and R2 up here. Now we assume a thin slice which is A, B, C, D. Okay, so these are two cross sections which are at very small distance apart. Okay, so they can be at a small distance apart, dx, or okay, let's not call it dx, but BD is a certain distance apart. We will work it out how much that is. But they are at a smaller distance. It doesn't mean that this BD is miles of distance apart. So we take two cross sections. Now after the application of the load, the beam will bend. Okay, so this is the bending profile of this beam. What will happen is that our AB and CD, okay, they will move in such a way that the top fiber, the top points which are AC, okay, the top AC distance, that will come, what will happen? That can increase, and this will decrease. The AC will come closer and the BD will go further. Or in other words, if we have a moment applied over here, and that moment will cause AC come closer and BD go further. Okay, so that's what's going to happen. Now, if I draw a parallel line to AB, okay, so I draw a parallel line to AB, but before that, these two, the two lines, the straight lines AB and CD, or these two cross sections, because they have moved apart, we can extend it and they will join at the same point. They don't remain parallel after the application of the load. Previously they were parallel. Okay? After the application of the load, they are not parallel. The top comes closer, the bottom goes further. So therefore we can extend these two and make them meet at a certain point O. Okay? So, and we say that the inclination, the angle subtended by these two lines is d theta. Okay, so now once this is established, then we can draw a line parallel to AB at point F. So let that be C dash D dash. So this C dash D dash is parallel to AB. Okay, so using geometry, we can say that this angle, the angle between CD and C prime D prime is d theta. Why? Because we have two parallel angles and they are crossed by a transversal. Okay, so this is a two parallel angle and this is a transversal which crosses it. So this angle will be equal to this angle. Agree? Now we will find out our strains, because stress is equal to E times strain. So E we would know already from this assumption. We say that material is homogeneous, so we know E. What we need to find over here is our strain, and once we put that in our equation, we will get our stresses. Okay, so strain is change in length So strain is change in length by original length. So the change in length. Now imagine we take a fiber, okay, which is at a distance y from the neutral axis. I told you what neutral axis is. Neutral axis is where your stresses are zero. Okay, so this is at a distance y from the neutral axis. So change in length by original length. What is the original length? The original length is the length of the neutral axis, because neutral axis has got no stresses. So therefore it doesn't get stretched or compressed. It will stay zero. So this distance, okay, that will stay as this one. Okay, so EF, so this will be the original length EF. This is our EF length, and the change in length is for this fiber. The change in length is HK. Change in length by original length. Agreed? Now, what is our HK? HK is y d theta, because S is equal to r theta. So this is y d theta. We can write, and we assume that the distance between point O, which is the intersection of these two lines, yeah, and the neutral axis is rho. Okay, that's what we assume. This is r, this distance is rho. So EF would be rho d theta. So this is y d theta and this is rho d theta. D thetas will cancel out and we will get y by rho. That is our strain. Now, stress is equal to E times strain, and this will be E y by rho. That is our fractional stress equation. Now tomorrow we will work on this equation and we will derive some additional equations. Okay, we will try to make use of these equations and some additional equations which are essential for ensuring equilibrium of the structure. Okay, so tomorrow in equilibrium we have 6 equations. There are 6 equations of equilibrium. Summation of all the forces in 3 directions and summation of all the moments in 3 directions. So every equation, if satisfied, will give us certain conditions. Okay, and those conditions we will study now. Okay, so do you have any questions about this one? Yes. Okay, thank you.